Hello and welcome to our video solution to problem 9 from Superquiz 3. In this problem, we would like to find the total charge of an electrical field inside of a given cylinder with a certain charge density function. So if one digs too deeply into these numbers, they might notice that the charge density function can be negative here, which doesn't make a whole lot of sense physically. Okay, so one can very reasonably criticize this problem for exactly that reason, but we're going to ignore the physical implications of such a silly problem and compute the total charge anyway. Let's start by drawing a little picture of the region. So it's a cylinder, but you'll notice it's not x squared plus y squared equals 49, but rather x squared plus z squared equals 49. So what that means is that the cylinder, its axis of rotation is actually the y-axis. So let's give a nice little picture here. So you have your x, your y, and your z. The y-coordinate is going to go between 1 and 5. So we'll draw those there. And then we're going to get our cylinder. So we'll draw circles at the end, and we can connect these up. And the radius of the circles on the ends is supposed to be 7. All right, so we're not going to worry too much about the scale here. But if we were drawing a radius here, that would have radius 7 coming from x squared plus z squared equals 49. All right, so we would like to set this up in cylindrical coordinates. So maybe we'll give a name to the cylinder. We could call it E. So in cylindrical coordinates, you have an r, a theta, and a z typically. But here, because we have rotated this cylinder so that its axis of rotation is the y-axis, we're actually going to switch this up. Right? It's the y-coordinate, right, which is sort of parametrizing where we are in the cylinder. We'll move the theta into what's normally our third component, right? Okay, let's see now. What can we say about the radius? Well, we know at each point in here, you're going to be what, between 0 and 7 units away. So we'll have r go between 0 and 7. Okay, that's just the radius of the circle. Remember the way you would normally do this is just project into, normally it'd be the xy plane, but here it'll be the xz plane. Right? So we would just project this big, all the points in the cylinder, it would just go into this disk, right, which is x squared plus z squared equals 49, where y is equal to 0. And I know in this disk, right, every point in here is within 7 of the origin. So that's how I get r going between 0 and 7. Now, I can quickly write down the y because that's given to us. And then the theta, well, because we get to go all the way around the cylinder, we know that theta will run between 0 and 2 pi. So this is how we're going to write down our region in cylindrical coordinates. We see it's actually a cylindrical box, which is fantastic because when we set up our triple integral, we won't have any dependencies on the variables. So r will go from 0 to 7, y will go from 1 to 5, and theta can go from 0 to 2 pi. And this integral, right, is going to give us the total charge. Okay, so we'll always write down what integral we're computing and then what it's actually equal to. So there's our total charge. And now we want our density function, rho. Only rho is written in terms of x, y, and z. So we need to convert those over into r, y, and theta. So when we switch to cylindrical, typically our x becomes r cosine of theta. Our y would become r sine of theta. But remember, we're switching perspectives here. It's now our z coordinate that acts like the y. So actually the z would be r sine of theta. And in cylindrical, y actually stays as y. So we don't have to change anything there. So our density function will become r cosine of theta plus y plus r sine of theta. All right, put some parentheses there because next is going to come our differential, which is normally dv in this situation. In rectangular, of course, that would be something like dx, dy, dz. But when you go to cylindrical, then you're going to get a dr, a d theta, and a dy. But also, you need the Jacobian, right? This cost of doing business. Okay, and that's an extra r. So we're going to get an r out front, and then we'll have here a d theta, a dy, and a dr. All right, we've set it up. That's actually the hard part. Now we can distribute this r in and see what we get. So let's see here. R goes from 0 to 7, y goes from 1 to 5, theta is going to go from 0 to 2 pi. Theta is going to go from 0 to 2 pi. So let's see, if we distribute this r, then we're going to have, well, there's two of these with an r in them. Let's make this r squared times cosine of theta plus sine of theta. And then we have plus yr, d theta, dy, dr. All right, so there's really two pieces here. We can handle them individually. Let's see. The r squared is just going to be a constant with respect to the theta and frankly with respect to the y, but we'll handle that when we get to it. So let's see here. When we integrate cosine theta plus sine theta, well, let's see. You're going to end up with a sine theta minus a cosine theta. So we'll have an r squared sine theta minus cosine of theta plus, okay, well there is no theta here, so it just becomes yr theta. And we'll evaluate this as theta goes from 0 to 2 pi. All right, well, let's see. At 2 pi and at 0, sine is going to be 0 and cosine is going to be 1. So this is going to end up being r squared times -1 minus -1. Okay, so this piece is going to be 0. All right, how about this one? Well, the yr is just a constant, so this is really just giving us the length of the interval. So we're going to get yr times 2 pi. All right, so actually all that stuff in there is just going to reduce down to 2 pi yr. All right, well, that means I can actually split this up pretty easily now. First, I can pull out the 2 pi. Then I can integrate r from 0 to 7, and we'll have an r dr. Then we'll have an integral y goes from 1 to 5, and we just have a y dy. All right, so these are pretty easy now. So we have 2 pi times, looks like r squared over 2 from 0 to 7, and y squared over 2 from 1 to 5, which will be, okay, let's see. 7 squared is 49 over 2 is 49 halves. At 0, you get nothing. And then 5 squared over 2 is 25 halves minus 1 squared over 2. So 25 halves minus 1 half. So this here is going to be 24 halves, which is 12. So let's see, the 2's cancel, so we're going to end up with 49 times 12 times pi. So 49 times 12 times pi, which is 588 pi. All right, so that is our total charge. Yeah, it didn't make much sense, the original problem, but hey, at least we got something positive, right?